So it is 12/7/15, a day that will live in infamy. You all know what that is a reference to. Okay, so you're being asked just to put things in order of increasing atomic radius, and you guys are really good at this going down a group. So down a group, not a problem. Across a period seems to be a little bit more problematic. So we talked about the fact that as we go down a period, atomic radius tends to do what? Point. Increase or decrease? It increases. They get bigger and fluffier. They have more electron shielding between the nucleus and those outer electrons. It's harder to pull those outer ones in. They get fluffier. But as they go down a group, as they go across a period, we have the same number of subshells. That doesn't change. But what does change is the number of electrons that are on those outer subshells pulling on the protons that are in the center. So we go, we have more protons in the nucleus, and we end up with more electrons on the outside. So there are, in essence, you can think about it in terms of like there are more places to get a good grip and pull on that outer shell, and so that outer shell tends to contract somewhat. And so as we go across a period, and the way I drew this was deceptive. Let's do that. So as we go across a period, atomic radius tends to decrease slightly. So if we're looking at any given period, let me pop in something from the periodic table here. In any given period, atomic radius decreases as we move that way. So neon we would expect to be smaller than oxygen. Oxygen we would expect to be smaller than boron. Neon smaller than oxygen. Oxygen smaller than boron. Boron smaller than lithium. So this is the thing that a lot of people missed. So for number 1, bromine, iron, potassium, arsenic, calcium, and nickel, that would mean that in order of smallest radius, bromine would be first, followed by arsenic, followed by nickel, followed by iron, followed by calcium, and potassium would actually be the largest radius in there. So I know a lot of people were putting the atomic numbers in there, and that's kind of misleading in this case, because even though we're adding protons and electrons, the radius actually decreases as we go across the period. This is the one that's a little bit counterintuitive. Okay, for number 2, let me wipe all that out. For number 2, we're sticking in one group. We're in the halogens. So smallest radius, and this is the one, everybody gets this, that radii increases as we go down the group. So fluorine is smallest, followed by chlorine, followed by bromine, followed by iodine. Iodine's a much bigger atom, and it's got many more shells on it. Okay. The next one was also a group. Like I said, people did pretty well with this. Beryllium is smallest, followed by magnesium, followed by, what did I give you? Oh, then I skipped calcium. I gave you strontium, barium, and radium. So again, order just goes same way it has been. Down the group, they get bigger. Okay, and then is the next one the tricky one? Well, the next one is one that a lot of people did miss, because it's, again, we're looking at a period, not a group, and that gets a little bit more confusing. So we're looking at this 6th period, and we're given radon, cesium, polonium, mercury, and barium. So the smallest atomic radius is always going to be over here, and that'd be radon, and then that would be followed by polonium, followed by mercury, then barium, and then cesium would be slightly smaller than barium. So that across groups is kind of, it's counterintuitive. You just kind of have to commit that to memory. Well, no, you don't really. If you think about the concept of electron shielding down the group, and you think about it sort of in reverse here, there are more places to get a good grip and pull in. They can hold them more tightly. Okay? The last one is the one with the trick in it. So in the last one, let me get rid of this. You are given boron, aluminum, gallium, and then calcium. What? How can you compare things that aren't in the same group? Well, it's not as hard as you think. So we know that of these three, which are all pretty close on the periodic table, we know that boron will be the smallest. We know that aluminum will be a little bit bigger than boron, and that gallium will be a little bit bigger than aluminum. Where would calcium fit into that? There's one of these where we have a known relationship to calcium. What is it? Gallium. Calcium we would expect to be larger than gallium because it's in the same period, but it's further over towards the alkali earth metals. So calcium would be our last one. Okay? Questions? Like I said, most people got 3 out of 5 was pretty common, 2 out of 5 was pretty common. I did have a few 5 out of 5s. Nice job. Okay, we're going to move on. Okay, so we're going to look at ionization energy. So let me ask you first, what's an ion? What's an ion? Jot something down. Write a description. Come up with a definition for an ion. Basically, an ion is just an atom that has a charge. It's not neutral anymore. And it can have a positive charge. It can have a negative charge. We're going to talk more about other names for positive and negative ions. But to make an ion, what do you have to do? There are 2 ways to make an ion. Give me one. Add an electron. Yeah. Because remember, atoms are electrically neutral because they have equal numbers of protons and neutrons. Protons and electrons, positive and negative charges. If we give an atom an extra electron, it's no longer balanced, so it's got a negative charge. What's the other way to make an atom charged? You have to disrupt that charge balance, so we could add an electron. What else could we do? Take an electron. We could steal an electron away from an atom. And the process of making an ion is called ionization. If you have an air purifier at home, there's probably a little button somewhere that says ionizer. It means it's creating ions out of atoms in the air, out of molecules in the air. So it's typically, I think, stripping electrons. It's got things that like electrons, and as air passes through, it strips electrons. You know, this whole thing about, positive ions. Whatever. So yeah, that's the process. And first off, we're going to talk only about making positive ions. So we're going to start with positive. To do that, you have to remove an electron. And this is, it may not be automatic yet, but it will be. Taking an electron away makes the atom positive. Why? Yeah, it gets rid of a negative charge. It's now got one more positive charge than it does negative charge. We call this the energy that's required to do that, ionization energy. So it takes some energy to pull, if I want to pull this off my desk, it takes some energy to do that. Removing things, moving things, period, takes energy. And remember, those electrons are held in place by what? Why are they there? Why Why are they there? What's holding them there? They're negative. The nucleus is positive. What's holding them there? What do we call that? It's an attractive force between opposite charges. So they're being held in place by this attractive force between opposite charges. The energy that it takes to overcome that attraction of the nucleus to those electrons is called ionization energy. Okay? Ionization energy. Alkali metals. Group 1. The group 1 elements. Sodium, lithium, potassium. They give up electrons easily. Why? You can go stretch your legs, get a drink. Could use a whole nother large vessel of coffee. I am. Yeah, I'm tutoring tonight. I'm here tonight. Mr. Voorhees and see if he has the reagents that I'm missing. Well, I don't have solutions for you to mix because I knew there was some stuff in the oxidation in the cabinet.
You don't have everything.
We don't have everything, and we're not doing it, and I am not ordering chemicals until they get me a chem supply closet that's locking in chemical resistant. Okay.
Okay.
So, I'm going to send an email. What the heck, I should have you just go show up, because that's what... Nothing. Don't say that out loud.
Go to Halogens?
No.
Go to...
Okay. So, of the 3 things marked missing, go ask Mr. Voorhees if he happens to have grabbed any of those at any point.
Okay.
Thank you, sir. I stayed up really late sewing Saturday night. This is my kind of wild and crazy at this point in my life. I was up until like 4 in the morning sewing something. Why? Because that's when everybody else is asleep, and that's when I can do it. I don't recover the way I used to. One night of really short sleep, and I am very disoriented. You know what? We are going to do some chemistry jokes today. Oh, yeah. I love chemistry jokes. Have you ever heard, do you even know who Garrison Keillor is? Prairie Home Companion? Okay. It's a radio show on public radio, and it's kind of like an old-fashioned variety show. So they have singing, they have little skits, and once a year they do what's called the joke show, and it is a solid 2 hours of joke after joke after joke after joke. Horrible, awful, wonderful, lots of puns, lots of knock-knock jokes. I love it. Love it. Okay, so lithium would like nothing more than to be like helium. Lithium would like nothing more than to be like helium. Oh, I wonder how long that's been recording. Good thing for the edit feature. So in order to be like helium, what does it have to do? Lose that electron that's sitting right here. That's got to go. And if that goes, then we go from having, and let me move this over, and I will copy the whole thing and paste it. And then we no longer have a lithium atom. We have a lithium, ion, shown as Li1+. And some sources just use a plus sign. I like putting in a number at all times because it's better to be precise. So everything in that first group, group 1, is really eager to lose an electron because then they can look just like the noble gas. So they tend to have very, very low ionization energies. It doesn't take a whole lot to convince them to give up an electron. This is like putting a plate of chocolate chip cookies in front of me. Do you want a chocolate chip cookie? Oh, twist my arm. Are you really going to have to convince me? No. You had me at, would you like? Yes, of course I would. That's about how group 1 behaves in regards to getting rid of an electron. They have very, very, very low ionization energies. Easy. Here comes the joke. Are you ready? So sodium is living in a bad neighborhood. It's rough. Maybe it's sodium's college days. I don't know. I lived in some sketchy neighborhoods in college. And there's gunfire outside. And sodium is hit. And sodium calls the police and says, help, help, there's somebody firing a weapon in my neighborhood. I've been hit. And they say, and sodium says, I've been hit. I've lost an electron. And the dispatcher says, are you sure? And sodium says, I'm positive. It lost an electron, so now it's positive. I've been hit. I've lost an electron. Are you sure? I'm positive. Okay. So anyway, you'll all laugh later. Group 1 is very eager to give up electrons. So if we're going to look at ionization energy, IE, it's really low over here. It does not take a lot to convince a group 1 element to give up an electron. They do it pretty readily. In group 2, what would a group 2 element have to do to be just like a noble gas? To be like the noble gas that we use to write its electron configuration with noble gas notation. You have to lose 2. So they give up 1 fairly easily, not quite as easily as group 1, but they still give them up easily, and you can even get them to take a second one, to give up a second one. Okay, and they typically do. They typically form a 2+ ion. So ionization energy is really, really, really low over in group 1, a little bit higher, but still pretty low in group 2. As we go across the periodic table, let's look at the halogens. Let's look at these guys. Fluorine has 9 protons, 1, 2, 3, 4, 5, 6, 7, 8, 9. I didn't draw them very well, but you get the picture. Fluorine has, it's 1s full. And then on the second energy level, it's got 2s2, 2p, 1, 2, 3, 4, 5. Now, it's a little bit different here. If you were going to draw the noble gas notation for fluorine, what noble gas would you use? You'd use helium again. So you'd use helium, and it's helium 2s2 2p5, but it's a whole lot closer to another noble gas. We don't write noble gas notations this way, but it's almost like, well, neon minus 1 electron. We don't write them that way. But in order to be, remember this is fluorine, in order to be just like a noble gas, it would be a whole lot easier for fluorine to gain an electron than to get rid of 7. So how likely do you think fluorine is to give up any electrons? It won't do it. You can't make a positive ion out of a halogen. They only form negative ions. They want to gain an electron. And just a word about language. I've heard this criticism before. In high school chemistry, and even to some degree in college chemistry, we tend to talk about, this atom wants to do this. This atom wants that. Atoms don't want anything. They don't want anything in the sense that we do. However, from an energy perspective, they tend to, again, I can't do it without using the word want. They end up in whatever arrangement makes them stable. So think about a rock on a sloped surface. Where does the rock stop? It stops where it's flat. It stops where it's stable. It stops where it's not going to roll any further. Atoms tend to end up in arrangements that are stable, where metaphorically speaking, they're not going to roll any further. Okay? So having 7 valence electrons is not stable. Having 8 is. But having 7 is like having a depression that needs to be filled. Until something rolls in there and fills it in, it's just not stable. It can't stay in that condition. Same for lithium. Having 1 valence electron out on that uppermost energy level is not a stable condition to be in. So it's, this is sort of the opposite. That electron is going to roll off. Once it does, everything else is in a stable position. Okay? But it's all about stability. It's about being, and there are really good metaphors to gravitational potential energy. That a bowling ball sitting at the top of a hill is not stable. So in essence, lithium with all of its electrons is like a bowling ball sitting on the top of a hill. Until that one last electron rolls off, this thing is not stable. And so once that disappears, once that electron is moved out, then it is in a stable position. So ionization energy is very low in group 1. Ionization energy is crazy high. Well, no, I shouldn't say crazy high. But it's really high here. So ionization energy increases as we go across the periodic table. Ionization increases as we go across a period. What? Pardon. IE high. Sorry. I'll make that a better... Nope, that looks like a W now. I thought that made it better. It made it worse. IE is high. So ionization energy increases as we go across. What did we say atomic radius did as we went across? Decreased. Why did atomic radius decrease across a group? Because the electrons were held what? More tightly. Well, does it make sense that if they're held more tightly and the atomic radius is smaller, it would be harder to pull one off? Yeah. Because the atoms on this end of the chart are holding their outer electrons much more tightly. And because of that, they're much harder to pull off. The valence electrons in these early groups, in group 1 and 2, are not held as tightly. And so they are easier to remove. Okay, well now let's talk about ionization energy as we go down a group. Based on what we just said about atomic radius and ionization energy, what would you expect to see in terms of ionization energy going down a group? Jot it down for yourselves. Let's think about ionization energy in terms of those outer valence electrons and how tightly they're held. So we said going across groups, as atomic radius decreases, they're held more tightly, ionization energy increases. What happens to ionization energy as we go, or what happens to atomic radius as we go down a group? It increases. They get bigger and fluffier. The further out those valence electrons are from the nucleus, do you think it's harder or easier to grab them? Further out they are from the nucleus, the easier it is to pull them off. They're not being held as tightly by the nucleus. They're more distant, they're more removed. Again, this is, to go back to the metaphor of the large family, I actually have a friend who is one of, I always want to say 18, and he's like, no, it's only 14. A lot of kids. And, he's joked because he and his wife have 2 kids, and he's like, I know everything my kids are doing all the time. My parents had no clue what anybody past number 2 was doing. Like, they didn't know. Yeah, they didn't know our middle names, As we get further and further out, there's less and less control. There's less tight hold. There's less of a tight hold. So atomic radius increases. These things get big and fluffy. And because they're not held very tightly, they're really easy to pull off. So as we go down a group, ionization energy, for any given group, where is it going to be lowest? Where's ionization energy going to be lowest for a given group? What do you think? Top or bottom? We know it's not the middle. Lowest ionization energy, is on the bottom. It's going to be easiest to pull electrons. It's going to be easier to pull electrons off of francium than it is off of hydrogen. I mean, it's still pretty easy. It's group 1, but comparatively, it takes less energy to pull the electron from francium than it does from hydrogen. Hydrogen, if you ask nicely, hydrogen will give you its electron. Again, these are metaphors. Francium throws its electron at you as it walks past. Okay? So, hydrogen gives it up easily, but francium, leaves it on your desk and walks away. As we go down a group, IE decreases. So IE decreases down a group. So let me ask you this question. Oops. I'm going to give you 2 elements. You tell me which has lower ionization energy. Nitrogen and arsenic. So nitrogen, and arsenic. Which one has lower ionization energy? Arsenic would have lower ionization energy. It takes less energy to pull an electron off of arsenic than it does off of nitrogen. Okay, copper and titanium, Ti. Copper and titanium, which one is going to have lower ionization energy? Titanium. Because remember, ionization energy increases as we go across a group. So titanium it'll be easier to pull an electron off of titanium than it will off of copper. Titanium would be more reactive. Okay. Barium and calcium. Who would have the lower ionization energy? Barium. Further down the group, lower ionization energy. Sulfur and aluminum. S and Al. Who's going to have lower ionization energy? Yes. Sorry, I didn't think about it. Yeah, aluminum's going to have lower ionization energy. It's going to take less energy to pull an electron off of aluminum than it will off of sulfur. Now, this is all, we've been talking about first ionization energy. Okay? We've been talking about first ionization energy. And we have, we said alkali metals, low IE. Halogens have they're really tough to get an electron off of. The hardest element in any period to get an electron off of is the noble gas. Noble gases are perfectly 100% stable. They have everything they want in life. They will not take an electron. They will not give an electron. They have the highest ionization energy possible. And that's what everyone's aiming for, is to be like a noble gas. Okay? They are totally stable. So if lithium gives up that one electron, it's just like a noble gas. It's reached a noble gas configuration. Guess what happens to an element's ionization energy when it reaches a noble gas configuration? It goes through the roof. Once you get to noble gas configuration, you're not giving up any more electrons. It's not going to happen. Okay. So we talked a little bit about the trends. What we have been talking about is first ionization energy. We can remove subsequent electrons. That's beyond the scope of this class. So there are some things that get 2 or 3 electrons removed from them. There are things, but we're not going to talk about them. We're really just talking about the trends in first ionization energy. Oops. Okay. This chart I really like. And I used to actually have students chart it. So if you look at these, how many elements are in that group that I just circled? The little squares actually represent an element. 2. That's the first period. So which elements is that? Hydrogen and helium. It's our first, and there's actually a little, there is a label on the axis. So we know that helium is going to have a higher ionization energy because it's a noble gas. Yeah. So then we go to the next group, and there are 8 in it. 8 elements. This is the what? It's the second period. So this is the ionization energies charted out by period. And what would be the highest ionization energy in the second period? You can use your periodic table. What would have the highest ionization energy in the second period? Neon, because it's the noble gas. What would have the lowest in the second period? Lithium. And hey, guess what? So as we go, now there's a little hiccup with beryllium and boron, and I don't know why. I don't understand why that is, but there are a couple little hiccups here and there, but in general, the trend is upward. As you go across a period, the ionization energy gets higher. When you get to noble gas, it's really high. And as we said, as you go down a group, it gets a little bit lower each time. Well, that's, there's the first period. There's the second period. What do you think that is? Third period. In essence, we're going down a group if we're looking at, the last thing in each. So we've got our noble gas up at the top. We've got our alkali metal at the bottom. And this only takes us down to 1, 2, 3, 4, the fifth period, but it's still a good indication. And hey, if you look real carefully at the bottom of this, cut all that stuff out. Get rid of this. This line down at the bottom, which is in a really light color, I know, is the atomic radius. So as this one goes up, this one goes down. As this one goes up, this one goes down. As this one goes up, this one goes down. What's the relationship between atomic radius and ionization energy? Math term here. What's a relationship where when one factor goes up, the other goes down? There's direct and inverse. Inverse. There is an inverse relationship between ionization energy and atomic radius. The larger the atomic radius, the lower the ionization energy, the easier it is to pull something off the outside. Again, back to my friend, with the 13 siblings. The larger the family, the less of a sort of leash that those younger kids are on. And I think he's like number 13. I think he's close to the tail end. Ionization energy increases, atomic radius decreases. Ionization energy increases, atomic radius decreases. It's a beautiful inverse relationship, and it makes perfect sense. The further out from the nucleus those valence electrons are, the harder they are to hold on to, the easier they are to remove. Okay, and hence the fluffier the atom is. Okay. Subsequent ionization energy, second ionization energy, third ionization energy, these tend to get bigger and bigger. The more electrons, so let's think about why that would be. Okay, so this is magnesium. 12 protons, 12 electrons, neutral atom of magnesium. And it's got those 2 on the outside. Now magnesium's group 2. It's got relatively low ionization energy. It's not all that hard to get it to give up some electrons. So we can get rid of, we can get rid of this electron. And now we have 11 electrons. So we now have 12 positive charges exerting an attractive force. So initially it's all fair in love and war, right? And it's 12 on 12 tug of war. 12 positive charges exerting a force on 12 negative charges. Well, now we have 12 positive charges exerting a force on 11 negative charges. That's not a fair fight. So removing that second electron, even though magnesium would be more stable with it removed, it still requires a little bit more energy. So the subsequent ionization energies tend to increase. Okay. Now, if we remove this second electron there, and we now have a magnesium 2+. So magnesium 2+, this is what magnesium wants. This is, I should say, this is how magnesium is most stable. We now have not only 12 protons pulling on 10 electrons, but magnesium has reached what kind of configuration? Noble gas. So guess what happens to its ionization energy? It goes through the roof. It's nearly impossible to remove another electron from magnesium. It's gotten to stability. It's not gonna budge. It's totally stable. It is really almost impossible to pull another electron. So the ionization energy tends to increase with each one you pull, mostly because of this tug-of-war thing. You have more protons now pulling on those electrons. But once you hit noble gas configuration, the IE goes through the roof. Ionization energy spikes. Okay? Ionization energy goes way up. Okay, so let's think about what this means in terms of reactivity. I don't know that there's a way to embed a video into Doceri, but let's go back and watch that video again, mostly because I love watching it. So, you know, watching nice guys with calm British voices blow up alkali metals. As you go down a group, ionization energy tends to decrease. It's easier to get them to give up that electron. Reactivity tends to increase. Those concepts are connected. What we will do tomorrow is finish like the last 2 slides talking about them. You're going to have time to practice these and work on homework. Homework's due Wednesday, which means test Thursday. So that's where we're at. I'll stop the recording now.